In August 2023, a team of engineers in a teardown lab sat staring at a smartphone they had just cracked open, and they could not explain what they were looking at. Inside the device was a microchip that the entire Western world had spent 6 years making sure could never be built. It was a 7-nanometer processor with integrated 5G fabricated entirely inside China by a company legally cut off from the most advanced manufacturing equipment on Earth. On paper, this heap of silicon was an impossibility. In their hands it was running. The device was the Huawei Mate 60 Pro, and its quiet release triggered an immediate geopolitical shockwave. For years, the consensus among global technology analysts was absolute. Without access to a highly specific, multi-hundred-million-dollar machine built only by a single company in the Netherlands, scaling the wall into advanced chip territory was a physical dead end. Yet there the silicon sat. But here is the part that almost nobody saw coming, the detail that the headlines completely missed. This phone was not the breakthrough. This was the warning shot. To understand why a simple consumer smartphone managed to rattle the highest corridors of power in Washington, you have to look at the sheer scale of the blockade designed to prevent it. In 2019, the United States placed Huawei on its entity list. The objective was not to slow the company down, it was to completely sever its lifelines. Overnight, a global technology giant lost access to the Google ecosystem. No Android updates, no Gmail, no Play Store. Shortly after, the trapdoor snapped shut on its manufacturing supply chain. Huawei was banned from using TSMC, the Taiwanese foundry that fabricated its cutting-edge designs. For a business heavily reliant on premium smartphones and global telecommunications infrastructure, this was widely considered a terminal diagnosis. By 2021, the strategy seemed to be working perfectly. Huawei's revenue collapsed by nearly 29%. Competitors began carved up its market share, and industry analysts were already drafting the company's obituary. The architecture of these export controls was engineered with a precise mathematical ceiling. The restrictions were explicitly designed to freeze China's domestic chip-making capabilities at what is known as the 14-nanometer node. In the world of semiconductor fabrication, a larger nanometer number means larger transistors, which translates to older, slower, and less efficient technology. A 14-nanometer limit meant keeping an entire superpower roughly a decade behind the global state-of-the-art. The linchpin of this entire strategy was an absolute monopoly on a machine called an EUV, or Extreme Ultraviolet Lithography System. Built exclusively by ASML in the Netherlands, this machine uses microscopic wavelengths of light to etch unimaginably complex geometric patterns onto silicon wafers. It is the only tool in existence capable of mass-producing chips at 7 nanometers and below. Because China was strictly banned from buying these machines, the global market assumed the ceiling would hold. You cannot build a modern skyscraper without a crane, and China did not have the crane. That is what made the silence of August 2023 so deafening. When the Mate 60 Pro materialized on store shelves without a single press release, independent labs rushed to dissect it. What they uncovered was the Kirin 9000S, a processor manufactured by China's domestic semiconductor champion, SMIC. Not only did it feature 5G connectivity, but it was built on a highly advanced second-generation 7-nanometer process. How do you build a skyscraper without the crane? You invent a completely different way to build. Denied the advanced EUV machines, Chinese engineers took older, less precise deep ultraviolet systems and pushed them far past their theoretical limits. They utilized a brutally complex multi-step technique called multi-patterning, essentially etching the silicon over and over again with microscopic precision to mimic the results of the banned machines. It is an engineering process that is incredibly difficult, highly inefficient, and massively expensive because it ruins a high percentage of the silicon wafers during production. But it worked. The phone contained over 10,000 individual components, and the vast majority of them were sourced entirely within China. Instead of being stuck 10 years behind the West, independent assessments concluded that the blockade had only managed to delay them by about 4 years. It was an embarrassing realization for policymakers. It was the geopolitical equivalent of tying a runner's shoelaces together, only to watch him figure out a fundamentally new way to run and still cross the finish line. Yet, a smartphone is just a consumer product. A phone was never the real objective of the massive domestic mobilization happening inside China. The Mate 60 Pro was simply the first thing they chose to let the outside world see. The true battleground was not shifting toward pocket-sized devices. It was aiming squarely at the technology that is currently redefining human civilization. Artificial intelligence. If a sanctioned, isolated enterprise could bypass a global technology blockade to build a premium consumer chip, a far more ominous question began to circulate through the industry. What happens when that exact same defiance, backed by hundreds of billions of dollars and a survivalist mindset, is aimed at the specialized hardware running the future of AI? The undisputed titan of that arena is NVIDIA. Its hardware is the bedrock upon which every major data center on Earth is built, and its absolute crown jewel is a system known as the GB200 NVL72. This is not just a chip. It is a massive liquid-cooled supercomputing rack that wires 72 of NVIDIA's most powerful next-generation processors into a single cohesive entity that behaves like a solitary giant brain. It is the gold standard for training the largest artificial intelligence models in existence. Huawei, still legally barred from purchasing NVIDIA's top-tier silicon, looked at this insurmountable lead and decided to build a direct competitor. On paper, it was an absurd proposition. Huawei's own flagship AI chip, the Ascend 910C, possesses roughly one-third of the raw computing power of a single high-end NVIDIA processor. 1 versus 1, the contest was over before it even began. Huawei simply could not manufacture a single chip dense enough or powerful enough to look NVIDIA in the eye. So, they stopped trying to build a better chip. Instead, they completely changed the rules of the game. They stopped focusing on the individual component and engineered a massive, systemic detour. The result of that shift was a monstrous configuration known as the Cloud Matrix 384, where NVIDIA relies on sheer concentrated brilliance inside a single rack. Huawei went for overwhelming coordinated scale. They did not build one rack, they built 16. They took 384 of their weaker Ascend processors and lashed them together using a highly sophisticated proprietary web of high-speed optical cables. By changing the architecture of how the chips communicate with one another, they forced hundreds of individual processors to function with absolute synchronization. When the engineering data for this system finally emerged, the performance metrics sent a second shockwave through the tech sector. The Cloud Matrix 384 delivers approximately 300 petaflops of raw computing power. NVIDIA's flagship rack delivers around 180. That is nearly 1.5 times the raw processing muscle. In terms of system memory, the critical bottleneck for handling massive AI datasets, Huawei's interconnected system boasts 49 terabytes, dwarfing NVIDIA's 14 terabytes. They could not build a faster thoroughbred. So they harnessed an entire team of workhorses to pull harder than the thoroughbred ever could. Of course, this workaround came with a massive penalty. The system consumes nearly 4 times the electricity of its Western counterpart. But in the grand scheme of geopolitical survival, efficiency is a luxury. Independence is a necessity. Huawei chose to burn massive amounts of power to buy absolute autonomy. By the summer of 2025, this system was no longer a theoretical blueprint. It was actively running live workloads on Huawei's corporate cloud infrastructure. Yet even this massive AI matrix is not the true monster in this story. The hardware is just the visible manifestation of a much deeper systemic shift. Because the most critical factor in this entire multi-year tech war was never a specific piece of silicon, nor was it a clever engineering workaround. It was a stark, explicit warning issued to American policymakers years prior, and it came from the one company with the absolute most to lose, as Washington was busy tightening the economic screws. Executives from NVIDIA repeatedly warned that a total blockade would backfire spectacularly. They argued that cutting China off completely would not freeze their progress. It would instead remove all incentives for them to buy American technology, forcing them to fund, design, and manufacture their own independent ecosystem. They warned that by trying to protect a monopoly, the West would inadvertently manufacture its most formidable competitor. That exact prediction has materialized. But the true irony of the story is that Huawei did not just react to the pressure, they anticipated it long before the first sanction was ever signed. The day after the 2019 ban took effect, an internal letter from the head of Huawei's chip design division leaked to the public. It revealed a closely guarded corporate secret. For years, the company had been quietly funding a shadow development initiative known internally as the spare tire strategy. They had been designing backup components, alternative operating systems, and independent network architectures for a decade, waiting for the day the trap would spring. The pressure did not destroy Huawei. It acted as an industrial forge, compressing a sprawling, vulnerable supply chain into a completely self-contained, highly resilient technological civilization. Today, the company controls its own AI chips, its own proprietary software architecture to rival NVIDIA's ecosystem, and its own independent operating system, Harmony OS, running on more than 1 billion devices worldwide. In early 2026, the final financial ledger for this 6-year campaign was made public. Huawei announced its 2025 revenue at roughly 880 billion yuan, approximately $123 billion. It was the second highest revenue figure in the company's history, pulling them right back to their pre-sanction peak and reclaiming the #1 smartphone spot in China ahead of Apple. The corporate entity that was supposed to be starved of technology had just concluded its most profitable era in half a decade. The blockade was meant to be an inescapable cage. Instead, it became the exact catalyst that forced the creation of a parallel technological universe entirely decoupled from the West. Huawei's current roadmap now aggressively targets a chip manufacturing density equivalent to 1.4 nanometers by the year 2031, which leaves the global tech industry staring at a reality that looks fundamentally different from the one planned in 2019. The pressure created an entirely independent supply chain that no one outside of China can monitor, regulate, or switch off. But as this new technological iron curtain drops, a massive flaw has just appeared in the foundation of China's new Silicon Fortress, a hidden vulnerability that has nothing to do with sanctions, everything to do with the fundamental laws of physics. To understand the deep structural flaw that now threatens China's newly forged Silicon Fortress, you first have to understand the sheer absurdity of the physics involved in making a modern microchip. When we talk about nodes like 7 nanometer, 5 nanometer, or the upcoming 1.4 nanometer targets, it is easy to treat them as mere marketing buzzwords. They aren't. They are measurements of scale that push against the very boundaries of manageable reality. A single nanometer is 1/1000th of a meter. For perspective, a human strand of DNA is about 2.5 nanometers wide. A single red blood cell is roughly 7,000 nanometers across. We are talking about carving structures that are hundreds of times smaller than a single virus. The tool that the Western world used to conquer this landscape is the extreme ultraviolet, or EUV, lithography machine. Think of an EUV machine as the world's most precise stencil and stencil cutter combined, using light as its knife. It generates a highly specialized wavelength of light, exactly 13.5 nanometers. By dropping microscopic droplets of molten tin through a vacuum chamber and blasting them with a high-powered industrial laser 50,000 times a second, this exploding tin creates a plasma that emits ultraviolet light. That light is then bounced off a series of the flattest mirrors ever manufactured by humanity, reflecting the light down onto a silicon wafer coated with light-sensitive chemicals. It etches billions of microscopic transistors onto a piece of silicon the size of a fingernail in a single incredibly clean pass. But as we established, China was entirely cut off from this machine. To survive, Huawei and its manufacturing partner, SMIC, had to rely exclusively on older deep ultraviolet, or DUV, machines. A DUV machine uses a much wider wavelength of light, typically 193 nanometers. To visualize the engineering nightmare this presents, imagine trying to draw a highly intricate, hyper-realistic portrait. The EUV machine allows you to use an ultra-fine technical pen with a microscopic tip. The DUV machine forces you to draw that exact same portrait using a thick, blunt Sharpie marker. On paper, it is physically impossible to get the same level of detail. The lines will bleed together, the features will blur, and the portrait will be ruined. So, how did Chinese engineers use a blunt linguistic marker to draw a microscopic masterpiece? They used a technique known as multi-patterning, specifically self-aligned quadruple patterning, or SAQP. Instead of trying to draw the ultrafine line in one single pass, the engineers broke the pattern down into multiple overlapping stages. Imagine taking that thick Sharpie marker and drawing a series of wider lines. Then, you chemically deposit a microscopic spacer material along the edges of those lines. Next, you wash away the original marker line, leaving only the ultra-thin chemical ridges behind. You then use those remaining ridges as a new, much tighter guide to etch another layer, repeating the process over and over again. By splitting a single complex circuit design into 4 separate hyper-precise exposures and chemical washes, they managed to stitch together lines that were narrow enough to qualify as a 7-nanometer class chip. It was a triumph of pure engineering willpower over hardware limitations. But this is exactly where the laws of physics stop being cooperative, and where the hidden vulnerability of the entire Chinese semiconductor ecosystem begins to expose itself. The fatal flaw of multi-patterning is not that it cannot create the lines. It is that it destroys what engineers call yield. Yield is the percentage of usable functioning microchips harvested from a single silicon wafer at the end of the manufacturing process. When TSMC or Samsung uses a modern EUV machine to print a 7-nanometer chip, the process is highly streamlined. The light passes through a single sequence, meaning there are very few opportunities for a microscopic speck of dust, a minor vibration, or a chemical misalignment to ruin the wafer. Their yields are routinely north of 80 or 90%. With Huawei and SMIC's quadruple patterning technique, the wafer must go through the machine, the chemical baths, the baking cycles, and the etching chambers 4 separate times just to print a single layer of features. Every single added step introduces an exponential risk of failure. If a machine misaligns by even a fraction of a single nanometer during the third or fourth pass, the entire batch of chips is rendered useless electronic scrap. Industry intelligence estimates that SMIC's 7-nanometer yield using DUV multi-patterning was hovering somewhere below 40% during its initial runs. That means for every 10 chips they attempted to bake, 6 of them were thrown directly into the trash. The only reason this was commercially viable is because the domestic market was heavily subsidized by a state that viewed chip independence as a matter of national survival. They were willing to pay any financial price to absorb the waste. But as Huawei pushes toward its ambitious goals of 5-nanometer, 3-nanometer, and eventually 1.4-nanometer architectures to power its massive cloud matrix AI systems, they are running headfirst into a hard physical wall. You can use multi-patterning to stretch a DUV machine from 14 nanometers down to 7. You might even be able to brutally force it down to a heavily degraded 5 nanometers using octuple patterning, aligning the pattern 8 separate times. But you cannot reach 3 nanometers or 1.4 nanometers this way. The structural alignment errors accumulate too fast, the chemical layers become too thick, and the yield drops to effectively 0%. You spend more energy and money destroying silicon than creating it. This means the spare tire strategy that saved Huawei from the initial shock of the 2019 sanctions has reached its absolute mechanical limit. The clever engineering workarounds that allowed them to build a $123 billion year and beat NVIDIA's flagship performance through brute force clustering cannot scale indefinitely down to the atomic level to bridge the gap to the next generation of computing. China cannot just rely on clever tricks with old Western machines. They have to reinvent the baseline physics of manufacturing itself. They need their own domestic equivalent of an EUV light source, their own atomic scale mirrors, and their own ultra-pure chemical resists built entirely from scratch inside a closed ecosystem. And that brings us to the quiet, frantic race currently unfolding inside hidden research facilities across Shanghai and Shenzhen. Because while the rest of the world was watching Huawei assemble massive racks of chips to outmuscle NVIDIA, a small group of Chinese physicists quietly proposed a radically different, almost science fiction alternative to the traditional lithography machine, a solution that bypasses the need for a compact ASML-style box entirely by turning an entirely different kind of massive industrial infrastructure into a chip factory. But to realize this radical vision, they have to solve a completely new problem. How do you stabilize a beam of light that is traveling at nearly the speed of molecules inside a machine that is the size of a city block? To find a way around that hard physical wall, Chinese scientists looked at the multi-million-dollar ASML machine and realized they were trying to solve the wrong problem. The entire Western semiconductor industry had spent decades trying to shrink a particle accelerator down until it could fit inside a standard factory room. ASML succeeded, but it required a machine of such staggering complexity that it contains over 100,000 moving parts and requires 3 Boeing 747s just to transport. Huawei and the researchers at Tsinghua University asked a deceptively simple question: why are we trying to make the machine small? Instead of shrinking the light source to fit the factory, they decided to build the factory around the light source. This is the radical concept known as steady-state microbunching, or SSMB. instead of blasting tiny droplets of molten tin with a laser 50,000 times a second inside a cabinet. The SSMB strategy uses a full-scale synchrotron, a type of circular particles accelerator that is literally the size of a city block. By accelerating electrons to near the speed of light around a massive storage ring and manipulating them with specialized lasers, the electrons bunch together into microscopic, highly organized clusters. As these clusters curve around the ring, they emit a continuous, incredibly high-powered beam of that exact, coveted 13.5 nanometer extreme ultraviolet light. Suddenly, you do not need 100,000 hyper-precise moving parts inside a tiny box. You have a massive stationary machine generating a giant steady river of EUV light. You can then build a spoke of clean rooms completely surrounding this accelerator, channeling that single, colossal light source to dozens of lithography stations simultaneously. It is the architectural equivalent of moving away from individual diesel generators in every home and plugging directly into a massive nuclear power plant. This pivot from micro-engineering to mega-infrastructure is not just a clever workaround. It represents a fundamental divergence in how humanity organizes its technological civilizations. For the last 40 years, the global tech ecosystem was built on the principle of extreme hyper-specialization. No single country, let alone a single company, could build a modern smartphone or an AI supercomputer on its own. The silicon wafers came from Japan, the software from California, the lithography from the Netherlands, the design from Shenzhen, and the fabrication took place in Taiwan. It was an incredibly fragile, hyper-optimized web held together by global trust. When Washington pulled the plug on Huawei in 2019, it effectively tore up that blueprint, and in doing so, it triggered a massive unintended evolutionary shift. By weaponizing the global supply chain, the West inadvertently forced China to do something no nation had ever attempted: build a completely parallel, vertically integrated technological civilization from the dirt up. We are no longer just looking at a rivalry between two competing tech companies like NVIDIA and Huawei. We are witnessing the bifurcation of technology itself into two completely distinct, mutually incompatible ecosystems. On one side stands the Western stack, built on hyperspecialization, high-efficiency EUV machines, and decentralized global trade. On the other side is the emerging Chinese stack, forged under the pressure of total isolation, powered by massive domestic infrastructure like SSMB accelerators, brute force clustering, and a state-subsidized tolerance for staggering inefficiency. And this is where the strategic calculations of the export controls stop making sense. The original architecture of the sanctions assumed that China would always play by the rules of Western market capitalism. It assumed that if you made a process too expensive or too inefficient, like multi-patterning with 40% yields, the target would eventually run out of money and give up. But what happens when the competitor is not operating on a corporate quarterly balance sheet? What happens when the competitor views the financial loss not as a business failure, but as the acceptable cost of national sovereignty? The result is that the economic gravity of the entire technology sector is shifting. Because Huawei was forced to build its own operating system, its own database architectures, its own networking protocols, and its own AI frameworks, it has created a closed-loop ecosystem that is entirely immune to Western pressure. Every time a new sanction is leveled, it no longer acts as a barrier. It simply functions as a massive guaranteed procurement order for domestic Chinese alternatives. This parallel stack is already expanding far beyond the borders of China. As Huawei exports its massive cloud matrix AI systems and its telecommunications infrastructure to emerging economies across the global south, it isn't just selling hardware, it is exporting a fully independent, alternative digital reality. It is offering countries a technological architecture that comes with a unique, powerful selling point. It is completely decoupled from American jurisdiction. It cannot be turned off by an executive order in Washington. The great irony of the 6-year campaign to strangle Huawei is that the blockade achieved the exact opposite of its intended goal. It was designed to preserve Western technological hegemony and keep China frozen a decade behind the cutting edge. Instead, by cutting off the pressure valves of global trade, it acted as an industrial centrifuge, separating the world's two largest economies and forcing the creation of a self-sustaining, deeply resilient competitor that no longer needs anything the West produces. The cage did not hold. The runner did not just learn how to run with his shoelaces tied. He redesigned the entire track, Which brings us back to the massive, liquid-cooled cloud matrix supercomputers humming away in the data centers of Shenzhen. Huawei has proved it can match NVIDIA's raw power through sheer brute force scale, and its physicists are already laying the concrete foundations for the massive particle accelerators that could render Western lithography monopolies obsolete. The hardware is built, the software is deployed, and the financial engines are roaring at $123 billion a year. But as this new, self-contained technological superpower prepares to launch its next major offensive into the global marketplace, a devastating new variable has just entered the equation, a sudden, unexpected shift in the global supply of a single, unglamorous raw material that neither particle accelerators nor mountain-sized data centers can replace. That indispensable raw material is not some exotic, ultra-rare element discovered in a deep mountain fissure. It is high-purity quartz, the literal bedrock of the entire semiconductor universe. To turn a piece of silicon into a 7-nanometer processor or a massive AI brain, you must first melt raw silicon at temperatures exceeding 1,400 degrees Celsius. This melting process can only happen inside highly specialized crucibles made from quartz of an almost impossible purity level, 99.999% pure. Here is the hidden irony that underscores the entire global tech war. The single most important deposit of this ultra-pure quartz on the face of the planet is located in a tiny quiet town called Spruce Pine, North Carolina for decades. The entire global chip ecosystem, from ASML in the Netherlands to TSMC in Taiwan, depended on a single geographic point in America for the containers needed to bake their silicon. When Washington built its technology cage around China, it assumed its control over the intellectual property and the equipment was absolute. But they forgot that nature has its own monopolies. As the geopolitical fracture deepened, the flow of these foundational materials began to seize up. But instead of crippling Huawei and its domestic partners, this final, resource-driven bottleneck triggered the ultimate phase of their transformation. Denied the pure American quartz crucibles, Chinese materials scientists did exactly what they did with the software and the lithography machines. They engineered their way out of the dependency. By investing heavily in synthetic quartz synthesis and opening up previously unviable domestic deposits, they secured the very base of their industrial pyramid. The final tether connecting China's technology stack to the Western soil was permanently severed. This brings us full circle to that quiet afternoon in August 2023, when a group of stunned engineers sat around a disassembled smartphone, looking at a piece of silicon that theoretically should not have existed. When you look back at the arc of this 6-year industrial conflict, the story stops being about a single company's survival and becomes a masterclass in the law of unintended consequences. The strategy of total technological denial was executed with absolute confidence. It was built on the logical assumption that a company cut off from the global supply chain, denied the most advanced machines on Earth, and, stripped of its primary revenue streams, would inevitably wither away. But that confidence was rooted in a fundamental misunderstanding of innovation under constraint. When you place a company or a nation in a state of absolute existential pressure, the traditional laws of market economics cease to apply. Efficiency is traded for survival. Capital ceases to look for the highest quarterly return and instead flows toward absolute resilience. By trying to freeze China at the 14-nanometer node, the Western world did not stop a competitor. It removed the only thing keeping that competitor integrated within the global system. As long as Huawei could buy chips from Taiwan and software from California, it had no reason to spend hundreds of billions of dollars rebuilding the wheel. By forcing their hands, the sanctions handed Huawei the ultimate market incentive, a guaranteed, captive domestic market of over 1 billion people who had no choice but to use their alternative. The result is a technological landscape that has split cleanly in two. The West continues to push the boundaries of hyper-specialized efficiency, building increasingly complex, fragile systems that rely on global stability. Meanwhile, inside China, a parallel tech civilization has emerged, one that is ruggedized, self-contained, and completely immune to external economic warfare. It is an ecosystem that runs on its own processors, orchestrates its data through its own AI software, coordinates its devices via its own operating system, and plans to manufacture its next generation of chips using massive, city block-sized particle accelerators. The $123 billion year that Huawei posted in early 2026 was not a fluke, nor was it the peak of their recovery. It was the proof of concept. The company that was supposed to be a historic footnote is now driving the adoption of an entirely independent digital reality across the globe. When we look at the modern world, we often assume that progress is a linear path, and that the most advanced tools will always win by sheer virtue of their elegance. But history loves an underdog victory, born of sheer defiance. The blockade was engineered to be a cage of absolute containment. Instead, it became the forge that hammered a vulnerable technology company into an unstoppable industrial competitor, and that is the single, surprising truth that most policymakers completely missed. In the high-stakes game of global technology, the greatest danger of trying to completely switch off your rival is not that you will fail. The true danger is that you will succeed so thoroughly that they will eventually build a world